Welcome to lecture 11 of Power System Protection course. So in lecture 10, in the previous lecture, we discussed about the implementation of IDMT relay, and also we have seen how we can discriminate the definite time over current relay and in case of use. So we have also seen where to use the definite time over current relay and inverse definite minimum time relay. So already we seen this, and then we talked about how we can implement these overcurrent relays in a three-phase feeder, and also we discussed about the directional overcurrent relay, why directional overcurrent relay plays an important role when the distribution feeder is being fed from both the ends, or if it is a mesh network, or if a single fed distribution feeder fed through two parallel lines or three parallel lines, how directional overcurrent relay plays very important role. Already we discussed all these things, and today we'll continue the directional overcurrent relay. We'll talk about how this directional overcurrent relay plays an important role and how it can be implemented in a three-phase distribution feeder. First we'll talk about the operational aspect, then we'll go ahead. Okay, so let us see it. So let us see the phasor diagram for voltage and current for forward and reverse fault of a single phase system. Already we talked about this and we'll little bit more emphasize this. So when a feeder is fed from both the ends, that is using the source EA and EC, both are being fed, both are connected at bus A and bus C. So we can see here one radial feeder that is supplied from two sources EA and EC, right? And now let us consider the fault at this point as forward fault. The relay is looking this fault as forward fault because the power is flowing from the bus B, because the relay is connected at bus B, and power is flowing away from bus B, so therefore this fault will be looked by this relay as forward fault. And the fault at this point will be the reverse fault. It will be looked by the relay in a reverse direction, so therefore it is the reverse fault. Now let us see the phasor diagram of the current, both the currents, forward and reverse currents. If we'll plot the VR as reference, taking the voltage seen at the relay point VR as the reference voltage, and the forward current, forward fault current, if we'll plot, it will be it will be very much, maybe it will lag, and it will be almost equal to 70-80 degree, right, lag by VR. And when we will plot IR, that is here the expression is mentioned here, IF forward, that is the forward fault current, that will be nothing but EA delta by ZSA plus ZAB plus ZFF. So ZSA is the source impedance at the location A, bus A, and ZAB is the impedance of line section AB here, and ZFF is the forward fault resistance from relay to the fault point. And this is the expression for IF forward. So similarly we can write expression for IF reverse fault, that is fault current in the reverse direction, that is nothing but equal to EC0. Here EC0 is taken, and the difference, angle difference between EC and EA is considered the delta, angle delta. So EC0 by ZSC plus ZBC plus ZFR. ZFR is the fault impedance in the reverse direction from location B where the relay is connected, and here from here to here, ZFR, and ZBC is the impedance of the line section BC, and ZSC is the source impedance of the source at bus number C. So if we'll plot these currents in the reverse direction and forward direction, the fault currents, we'll see that there is a phase difference of approximately equal to 180 degree. So that means it is approximately equal to 180 degree. So that means it is opposite to the forward fault current, right? So now let us see the directional overcurrent, the characteristics of directional overcurrent, and already we have seen in the last class also, right? So here it is a relay, directional relay is shown here, and it is fed by CT, that is current at the relay location, right? So here the current is being fed at relay location IR, obviously it is from CT, and here the voltage is being fed, right, from relay location, that is VR, right? So the voltage is being fed to pressure coil, and the current is being fed to the current coil. Now let us see the phasor diagram. Already we have discussed this in the last class. Okay, so see, let us see the phasor diagram. So the phasor diagram, here we can see, if we'll plot the VPC considering it as phasor as a reference, then with respect to VPC, if we'll plot IPC, it will make an lagging phase angle. Maybe it is around 90 degree, not exactly 90 degree, it may be around 70 degree or 80 degree, because the coil is an inductive coil. It's an inductive coil, therefore it will make an angle of 70 or 80 degree. So with respect to this, already we discussed, this is the position of ICC for maximum torque. Already we have seen this, right, how it came in the last class we discussed by deriving the operating torque, and from here, from the operating torque, we found that the angle between this IPC and the position of ICC should be 90 degree, and we considered the angle between VPC and position of ICC for maximum torque as tau, which is called the maximum torque angle. So this is called the maximum torque angle, and it is sometime also in short we call it MTA. And this angle can be it can be adjusted using these two variable parameters. One is variable capacitance and other one is variable resistance. By adjusting this, we can adjust this maximum torque angle all the time, right? Because by adjusting these two, we can adjust this theta PC. As theta PC will be adjusted, then this maximum, because this will also, as this will move, then your position of ICC for maximum torque will move, and hence your maximum torque angle can be adjusted, right? So therefore we can see that this is your maximum torque angle is tau, and your ICC is plotted here. Now let us see if the current reverses. So what will happen if the relay will detect or not? Okay, so if the current will reverse, we can see here it will just reverse, means it will be here, right? It is ICC in the negative direction or in the reverse direction, right? So I can mark it as ICC reverse. So what is the angle it is making? We can see here the VPC, with respect to VPC, it is making more than around more than 270 degree, right? So more than 180 degree, right? So we can see from here that, and also the phasor, that is the reverse current, is lying in the restraining zone. Why it is restraining zone? It is called restraining zone because just substituting this value, let us substitute here. What will be the angle here? It will be 180 plus theta, right? So theta is this, and here also it will be theta. Okay, now it will be if we'll substitute the angle instead of theta, we'll substitute 180 plus theta. Now your operating torque will become what? It will be T operating will be A2 VPC IPC cos of 180 plus theta minus tau, and it will be minus, right? Minus K2 VPC IPC cos of theta minus tau. Okay, so it is producing a negative torque which will restrain. Okay, so therefore this whatever wherever the current will lie here, right? So it will become in this zone, wherever it will lie, it will become it will restrain. The torque will be negative and it will restrain. The relay will restrain. So therefore this region is known as restraining zone, right? And whatever current phasor will lie in this trip zone or trip region, we'll see that it will produce a positive torque, and therefore it will be the trip region. Okay. So let us see the application of directional relay to a three-phase feeder, how we can analyze this application of directional relay to a three-phase feeder. So the directional relay must meet the following requirements. Okay, so the relay must operate for forward fault. First condition or first requirement is it should operate for forward faults. And second requirement is the relay must restrain during reverse fault. Okay, these are the requirements of directional overcurrent relay. And third one is the relay must operate during faults other than for which it has been provided. Must not operate, sorry. Relay must not operate during faults other than for which it has been provided. That means the relay must not maloperate, right? So these are the three main requirements of directional overcurrent relay. Now let us see the directional phase fault protection. So consider a directional relay for protection against all phase faults. So what are the phase faults? Already we discussed. Phase faults means the faults which are involving more than two phases, right? That is called phase fault. So then we can say that A to B is a phase fault, A to B to ground, A to C to ground, A to B to C, and A to B to C to ground fault. They are all categorized as phase faults. Now let us consider a fault which is between phase A and B. Okay, and we have a directional relay here. Now the question is what parameter we should feed to the, here let us say this is the signal to the pressure coil and this is the signal to the current coil. Now the question is what parameter will feed, or what measurement signal will feed to the pressure coil and what will feed the current coil. Current coil obviously will feed the current. So if the fault is at the phase A, phase B or phase C involving all these phases, will take the currents from one of the phases in which the fault happened. And what will be the voltage? Because we have many voltage options, right? We have VAN, right? We have VAG, VBG, then VCG, then VAB, then VBC, then VCA, right? or VAC. We have a lot of options, VBA, VCB, right? Or you can say VCB or V, right? So there are a lot of options we can have. So then which one will choose? This is very important. So let us see how to choose the parameters or how to choose the measuring signals to the relay. Okay. So let us first consider IA. Sorry, this will be your CC, current coil, and this will be your PC, okay, pressure coil. So now let us choose the current IA to this current coil and voltage VAB to the pressure coil, and let us see whether it is working for a fault involving phase A, that is AB fault, right? So that is the fault between phase A and phase B. So let us see then. So now we can see here the phasor diagram for all the current and voltage phases, and here we can see that this is your VA and IA in the same phase. That is called the unity power factor position for the current, and the load here assumed is unity power factor. Okay, and your IB is lying with VB, IC is lying with VC. These are the phase voltage and phase currents. Now, if we'll draw the line voltages, VCA will be in this direction, VBC will be in this direction, then your VAB will be in this direction, right? Now, if the fault happens, what will happen? Suppose the fault happens in phase A and B, they're sorted together. Now the fault current which is flowing in phase A will be very high. The magnitude will increase suddenly, and the angle it will make with respect to VA will be around 90 degree. Okay, it is not exactly 90 degree, it will be maybe 70, 80, 85 degree. Okay, because it becomes inductive the arc. So therefore it will make an angle of around 90 degrees. You can see here in the phase, right? Phasor diagram. And also the magnitude of VAB will decrease in the same direction as VAB. Okay, so it will decrease. The magnitude we can see here, now it became this much. So this is your VAB. So that is VAB fault, under fault condition. And current will increase. Already we have discussed this in the first or second class in the previous classes, right? So now let us see whether if we'll feed VAB to the pressure coil of directional relay and IA to the current coil of the directional relay. So what will happen? Whether this relay will trip, whether this relay will give a trip signal to the circuit breaker or not. So now we can see here, let us plot all these phases. Let me plot VAB fault, that is in this direction it is plotted. And now if we'll plot current that is before fault, that is under unity power factor condition, your IA will be this. And now your fault current will be around 90 degree with respect to your VA or VAV fault rate. So it is around 90 degree, not 90 degree, VAF forward. So now if we'll plot the empty line, that is the position of ICC for maximum torque. This is the maximum torque angle line, empty line. So what will happen? How it is plotted? Your current flowing in the PC coil will be, maybe it will be around this point, right? Okay, so this line. So it will be your PC, IPC. Okay. So current flowing in the pressure coil, which will lie in this line, right? Which is equal to, which will make an phase angle of 90 degree to the empty line, right? Now we can see here your IAF is lying outside the trip zone or trip region, that is in the restraining region, right? Okay, so therefore it will not trip. Okay, so therefore this will not work. That means when we feed VAB to the pressure coil and IA to the current coil, this will not give a trip signal to the circuit breaker. It will not trip, the relay will not trip, right? Then let us see the reverse current IAF, and which is lying in the trip region. And for reverse current, reverse fault current, this relay will operate. That means it will mal-operate. So therefore this kind of arrangement, that means we should not feed VAB to the pressure coil. Now let us consider this is your MTA, tau, right? We can see here tau is your MTA, right? So this angle is your maximum torque angle. Now if we'll see another condition, another measuring signal, we'll take, let us say VCA will consider and will feed to the pressure coil and IA to the current coil. Okay. So under that condition, what will happen? This is your phasor diagram already we talked about, and let us plot the VCA fault. So VCA fault will be here, right? This will be your VCA fault. Under fault condition, the voltage VCA, and this is your unity power factor IA, that is IA at unity power factor position, and IAF will be here in this region, already we have seen here, right? And if we'll plot now the MTA and corresponding IPC, right, or ICA. So MTA line will lie here, right, because this current through the pressure coil will be around here in this region, right, that is IPC. So this will make an angle of 90 degree to MTA. So this will be your MTA line. Okay, now this will be your trip region, right, and this will be your restraining region, and where from here, from the phasor diagram, we can easily see your IAF, that is the forward fault current, is lying in the region, restraining region, and in fact the reverse current is lying in the trip region, which is undesirable. So therefore this kind of connection is also undesirable from where we are feeding the VCA to the pressure coil, right? So we have another option left, that option is VBC. Let us check it with VBC whether it works or not. This is your MTA, okay, maximum torque angle. Now let us see the another option, that is IA. Automatically it will be fed to the current coil, and to your pressure coil let us feed VBC, that is the voltage across B and C. So from the phasor diagram, your VBC is here, right? This is your VBC. So this in this direction, right? So now let us plot the phasor diagram, and phasor diagram for the relay, relay operating conditions. We can see here, if we plot VBC, sorry, VCA is this, right? So VCAF. So okay, so let us plot the phasors. Now plotting VBC. VBC is obviously, we can see here the VBC is it is parallel to it is obviously making an angle of 90 degree to VA and IA, that is before the fault, and your UPF IA, that is the IA under unity power factor condition before fault, will obviously make an angle of 90 degree, right, to VC. This VBC is your voltage before the fault, right? Now if we plot the VBC under fault condition, that is VBCF, obviously it is leading here, right? We can see here it is leading, right? So therefore here it will also lead to VBC before fault, right, by some angle, and obviously the magnitude of VBC F will also decrease. And if we'll plot IF forward, it will be here. Somewhere here from this condition, right? Now if we'll plot the MTA line, we can see here empty line will be obviously, it will make an angle of 90 degree, it will make a 90 degree to the current flowing in the pressure coil, right? This is your IPC, sorry, this is your IPC, right? So it will make an angle of 90 degree to IPC, and so this is your MTA, this is your MTA tau, right? And if we'll plot IF reverse, it is obviously it will be opposing, it will be in the opposite direction to IF forward, in the forward direction. So now we can see that the forward fault current is lying in the trip region, and IF is lying in the IF reverse is lying in the restraining region. That means this condition, that means this kind of connection is suitable for detecting the fault that involves IA and B. So between A and B, that means if we'll feed the current to the current IA to the CC current coil and VBC to the current coil. Sorry, this is your PC. Sorry, PC. Okay, this is your uh, BBC to the pressure coil. Okay, now that means we can conclude that your BBC, which is lying, we can see here lying 90 degree lagging to the UPF IA. So therefore this kind of connection is known as 90 degree connection. Okay, so this is in the literature, this kind of connection is known as 90 degree connection. So this 90 degree connection is suitable for this degree connection is based on the voltage and current position before the fault occurs, right? So therefore before the fault the position of UPF IA is this and your BBC is this, that is BBC is making an angle of 90 degree lagging to IA, UPF IA. So therefore this connection is known as 90 degree connection. Okay, so this is, I think is so we can conclude that 90 degree connection for each of the phase fault is suitable. And other kind of suitable connections also we can see here. We can see here at the different phase faults involving phase A, phase faults involving phase B, and phase fault involving phase C. So now we can summarize what kind of connection we'll consider for different types of phase faults. Now phase fault involving phase A, for that we'll choose current IA, for which will be fed to the CC through the current coil, and we'll choose voltage in different wave. Already we have seen we'll choose voltage VVC, which is making an angle of 90 degree lagging. So that type of connection we call it 90 degree connection, right? Okay, and second also will be suitable if we'll connect IA and VAC. This is another type of connection. This will also be suitable. You can test by doing the phasor diagram. Please do it in your home because it is important. It may come in your sometime I will give as assignment or in your exam, right? So if we'll connect IA to the current coil and VAC to the pressure coil, then obviously the angle between IA and VAC, that means VAC is making an angle of 30 degree lagging to IA. If we'll go back and we'll see the phasor diagram here, we can see here your VAC will be in this here, right? This is your VAC and this is your IA. So that means your VAC is making an angle of 30 degree, right, lagging to IA. So therefore this kind of connection is known as 30 degree connection. Okay, when we connect IA to the current coil and VAC to the pressure coil, this is known as 30 degree connection. Then another type of connection is also suitable, that is if we'll add VAC and VBC together and we'll feed this summation, sum of these voltages to the pressure coil and IA to the current coil, then this will also act, this will also give the trip signal when it is in the forward fault condition, and it will restrain in the reverse fault condition. So this is in fact VAC plus VBC. If we'll see the phasor diagram, VAC plus VBC, this will make an angle of, here it will be VAC plus VBC, right? So this will make an angle of, this is your IA, right? This will make an angle of 60 degree, right? So therefore this connection is known as 60 degree connection. So these two 30 degree and 60 degree connection, you can check the phasor diagram at home, and if you will have any doubt, you can ask me. So similarly, the phase faults involving phase B, obviously we'll choose the current IB for this current coil, and for pressure coil we'll choose VCA because VCA is making an angle of 90 degree lagging to IB, and that is known as 90 degree connection. And similarly, to make 30 degree connection, we will choose IB and VBA. So that will give us 30 degree connection. And similarly, we'll choose for 60 degree connection IB for the current coil, and VBA plus VCA, that will be fed to the pressure coil, which will, this sum of the voltage will make an angle of 30 degree to IB, 30 degree lagging to IB. So therefore, as 60 degree. So therefore, this will be known as 60 degree connection. Similarly, for phase faults involving phase C, the current obviously will be chosen as IC, and for current coil, and for pressure coil for 90 degree connection, BAB will be chosen. For 30 degree connection, VCB will be chosen, and for 60 degree connection, it will be VCB plus VAB, right? So these different types of connections you can check at your home, and if you will have any doubt in doing this checking, doing the phasor diagrams, you can ask me in the doubt class. Okay. So now we'll see the directional ground fault protection. So already we covered how the directional overcurrent relay can be implemented for the phase faults, right? Now let us see how it can be implemented for the ground faults. So what are the ground faults? We have ground faults. Three types of ground fault: A to ground, B to ground, and C to ground, where only single phase to the ground is involved, right? So these are known as the ground faults. Now let us see how we can implement the overcurrent relay for ground fault. So obviously under uh, this condition, when this is a unbalanced condition and single phase to ground fault is more frequent, and if we'll put one of the relay coil in your neutral wire, that means where we can detect the zero sequence current, we can easily find the ground, we can detect the ground fault, right? Similarly, for voltage also, for the pressure coil also, if we'll add these three voltages, VA plus VB plus VC, we can easily find. So that is equal to nothing but equal to 3V0, right? Zero sequence voltage, and IA plus IB plus IC, which is the neutral current, right? Neutral to ground current, which is equal to also 3I0, right? And if we'll feed these these quantities, summing the voltage to the pressure coil and summing the current to the current coil, then easily that means in order to find this current, just we need to put, or we need to detect this zero sequence current. Okay, if after detecting the zero sequence current, it is uh, very easily we can say the fault is there. And VO, how we'll find? Just by adding these three voltages, VA plus VB plus VC. So therefore we are feeding 3 VO and 3 IO both to the directional relay. Now if you see the phasor diagram, your fault current will be here somewhere. Let us say if the fault is from A to G, let us consider the fault is A to ground, Okay, so now considering phase A to ground fault, your fault current will be here somewhere, right? And IF equal to 3I not here mentioned because we are detecting this neutral current, right, by putting a CT in the neutral wire. Then your VA will reduce drastically, right? So VA will be EA minus IA ZS, because ZS is your source impedance, and your EB will remain same and EC will remain same. So now if we'll see the phasor diagram in your relay phasor diagrams, then how it will look. So we are feeding the voltage. What voltage we are feeding? 3VO, right? So 3VO we are feeding. So how we'll find 3VO? That is VA plus VB plus VC, and that will give us 3VO. And with respect to 3VO and the current in the pressure coil, this will be your current in the pressure coil. This will lag 3VO, right, around 90 degree, not exactly 90 degree. So therefore uh, your empty line will be making an angle of 90 degree to the pressure coil current. Okay, and your 3I naught is really here, which is in the trip region, right? 3IO, and your reverse current 3IO reverse is it is opposite to 3IO forward, and it is just laying in the restraining region, right? So therefore in this way we can detect the ground fault, and you can implement the uh, directional relay for detecting the ground fault, and it will be implemented for the ground fault protection. So we'll stop here, and in the next class, in the next lecture, we'll talk about how we can implement this directional overcurrent relay in a three-phase feeder. Then we'll complete the overcurrent relay part, and we'll start the distance relay. So thank you very much for your kind attention. So thank you, thanks a lot.